Last time we started with waveform encoding. And remember what waveform encoding does. It looks at the signal as it comes. It doesn't necessarily care what the signal is. Beyond the bandwidth of the signal, it knows what its sampling frequency is, and then digitizes that signal, treating it only as a waveform. Now you may want to ask, well, what's the alternative? Alternative is when you do analysis of the signal. And a lot of times we have tremendous benefit that we gain from it. Typically, I mentioned it several times, in a high compression scenarios, we do exactly that. If you look at transmission of the voice in pretty much all the contemporary systems, what we do is we analyze the voice instead of just sampling and quantizing and all of that, but we do what is called linear predictive coding and vector encoding. And by doing that, we are able to shrink the voice from nominally, as you've seen, 64 kilobits per second to something that is sub 8 kilobits per second, realizing gains of 10 times in a compression of the data rate by doing this more sophisticated method. Now, this is not waveform encoding. This is encoding by analysis of the signal. And it has its drawbacks too, because if the system is made to transmit voice, it's not very good for any other signals. And you can sense that. Try replaying music through a cell phone. It's very poor quality, right? And the reason is because cell phone doesn't understand its music. It thinks it's voice and tries to use the same algorithms that is used for compression of the voice on the music itself. So last time we talked about PCM. That's the straightforward application of the sampling theorem. You sample, you quantize in time domain, and then you do the quantization in amplitude domain, turn these numbers into bits, and that's what you transmit. Today we're going to talk about delta modulation. That's yet another way how you can actually digitize the signals. Delta is, in some respects, simpler than a PCM. It's essentially you will see it is simpler and it is more robust. And what happens is in noisy environments that require that your encoding scheme is robust, that's where we use delta modulation. Both of them are still in use today and in quite a few systems. So let me say here delta modulation. And the symbol is delta modulation, delta E. So let's first discuss the idea. Here's the drawing of what is meant by the delta modulation. Here's your signal that you're trying to decode, and here's the times when you take the samples. In PCM, what we do is we treat each sample as a value on its own, and we encode every sample individually. Now, if you look at most signals, the difference between the two samples is not always that large. There is what we call redundancy in the signal, and that's true for all natural signals. When I speak sentences, and the sentences have a logical flow of the signal levels, right? You cannot be speaking here and then next here and then after that over here, right? This is not how the speech is. And so there's a lot of redundancy in signals. Again, the best thing is if you take a speech signal, you know very well that if I took a portion of what I'm saying and I cut it out, you're still going to be able to understand quite a bit of what I'm saying, because there is redundancy in the speech itself. So how do we use that to our advantage? Well, if instead of trying to encode each individual sample, I say, well, how much is novel in the following sample? In other words, I'm looking the sample in the previous one, and instead of encoding this, I look at just the difference, the delta between them, and I encode that delta. That's the idea between delta modulation. And in its basic implementation, it is the simplest as can be. Instead of instead of looking, all I'm actually going to say is whether the next sample is larger or smaller than the previous one. That's the basic implementation of the delta. Now, this can obviously be implemented only if I sample at the rate that is fast enough so that the difference between the two adjacent samples is not large, right? And we're going to have to establish that in more precisely. So what I'm going to do next is let me draw here a schematic of how the delta modulator would look like. How would I actually go from the signal to encoding the delta between the samples, and then we'll walk through the modulator and put some math to it. And what we need to find out in the end is how do you actually do this, and then the second thing that we will need to find out at the end, just very much the same thing we did in the case of the PCM, quantify the signal to quantization noise ratio in a delta modulation as a primary metric of how good this modulation scheme is before you put it into the channel. So let me draw a modulator here. So here's your input signal. There are a few blocks here. Let me draw them and then we'll comment. The first element here is something that we call limiter, which is going to actually either generate plus or minus delta. And there is here pulse generator that generates the series of delta pulses, x0 of t. And then there is an integrator here. There's an x hat of t. Then the signal here is x dm of t delta modulated signal. And this is PSF, this is pulse, PSF, stands for pulse shape input. All right, so that's and this is where it goes into the channel. Okay? So let's kind of write the equations surrounding each one of these signals that we identified in the schematic. First, I'm going to start with this signal here. XO of t is pulse train. Let me put here pulse train. And it is something that is sum when k goes from minus infinity to plus infinity, delta of t minus k ts. This is essentially train of delta pulses. You know, in a practice it cannot be that, and I'll discuss that a little bit later, but from the theoretical standpoint, let's assume that this is just pulse of deltas. This ts here is a sampling period. Now, sampling period here is substantially smaller than a Nyquist sampling period. What in a Nyquist sampling period, so this is this TS. In a Nyquist sampling, TS had to be smaller than 1/2 times the band, right? And this is essentially, you know where the root of that is. The root of that was so that you don't have aliasing in the frequency domain. Now, sampling here needs to be fast enough so that the change in adjacent samples is smaller than delta. And that will derive that, and you will see that substantially smaller than a sampling in accordance to the Nyquist sampling rate. Now, let's take a look at this. This is limiter. So let's, I think there are two keys. So let's look at the transfer function of that. You have a transfer function y of x is equal to plus delta if x is greater than 0 and minus delta x smaller than 0. So it's a very simple device. All it cares is the sign of this difference here. So this is plus minus. It will take these two signals, compare them. If the result is positive, it will put the plus delta here. If the result is negative, it will put minus delta at the output here. Now, if now I look at this signal here, x dm of t. This guy will be sum when k goes from minus infinity to plus infinity, dk delta of t minus k ts, where this dk is either plus delta or minus delta, right? Because if you see how does this one originates, is whatever is coming out of this limiter is multiplying the pulse train. So it's multiplying this signal here, and this can be either plus delta or minus delta, so you're going to have either positive delta pulses with the area under the curve equal to plus delta, or negative delta pulses, which will have the area under the curve equal to minus delta. So this is this signal x dm of t that we're going to send at the output of this multiplier here. Let's take a look at this signal x hat of t. X hat of t is essentially, this is the same signal here, is going to be integral from minus infinity to some t of x dm of t dt. In other words, this becomes sum when k goes from minus infinity to plus infinity, dk integral from minus infinity to t delta of t minus kts dt. What is the integral of delta function? 1. Is it 1 or something that starts with s? And then step.
Yeah,
Right? It's not 1, right? 1 goes from minus infinity to plus infinity. Step function is the integral of delta, right? Before delta it's 0, after delta it's 1. So this is now sum when k goes from minus infinity to plus infinity, dk times u of t minus k ts. So this is the signal x hat of t. Now the question is, what is that signal? One more thing that we can use to rewrite this slightly different is we can say this is k is from minus infinity to plus infinity. Now what is this dk? dk is the sign of the difference between these two. So you can say that this x hat of t is delta times sine of x of t minus x hat of t, and then times u of t minus k ds. Now all of that is still math, so let's look at a little bit graphically what is it that we're doing here. So what I'm going to do is try to draw all of this. So this is time t. Now let me draw some of these signals. And time t. So this is x0 of t. And let's look at, this is x dm of t. So what I'm going to, just like I did over there, I'm going to start first with x0 of t. x0 of t is just a train of pulses, right? This is my sum
is a sum when k goes from minus infinity to plus infinity, delta of t minus k ts. Obviously, this difference here is ts, and each one of these represents a signal delta. This is the signal that comes out of here. Right. Now, let me draw my original signal. So let's say this is my x of t. So let's start with, this is my signal here, x hat of t. Let's say it starts from 0. So let's see what happens. If x hat of t is equal to 0, then sine of x of t minus x hat of t is what? It's, look at it over there. X hat of this is 0, so it's x hat of t. Sine of that is equal to 1. So this becomes delta. So my x hat of t jumps here to, let's say delta, 2 delta, 3 delta, 4 delta, and let's just make sure I put these TS's here. So at this point, it will jump to delta, and then stay as delta. Now at this point, it will compare against x hat of t against x of t, and then it will say, okay, well, is x hat of t greater than x of t greater than x hat of t? Yes. So I add another delta, and every time I add delta, I'm actually adding a step function. See, this is the previous delta, this is this one. Every time I'm adding a step function that, that has a magnitude delta. So I'm here. At this point, what happens? Again, x of t is compared with x hat of t. X hat of t is lowered, so it is commanded to jump by delta. So now I go here, then I stay like that until the next one, then I jump, then I stand, then I jump, then I stand here. Now what happens at this place? At this place, x of t is smaller than x hat of t, and therefore the sign here becomes negative. And then what I'm going to add is another step that is now in the opposite direction. So you go and do this. I'm kind of diverging. Let me bring me back to here. Then you do this. Maybe something like this. So at this point, you're gonna be, let's say, okay, so this is what is happening. This signal here is x of t, and then this signal here is x hat of t. Okay? So you get the idea what the delta is doing. It is, I should have really put here the x dn, this signal here, because this one is going to just have delta dk times delta. So in this case, it was positive, 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 then here negative, positive, negative, 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 and so on. So this is our x hat of t. This is x of t, this is our chain of pulses, and this is essentially what we try to send on the line. What we're trying to send on the line is actually this, but ran through this pulse shaping filter. What the pulse shaping filter is going to do is it's going to turn these delta pulses into something that you can actually transmit over the line. So these are going to be either Gaussian pulses or some sort of rounded square pulses or whatever is the pulse that we decide to send over the line. So this is transmitted actually if I add an another one here. And let's call this signal X channel of T. So what this one will do, it will take, for example, each one of these and send something that is more appropriate for, well, still possible. Okay, so this is our X channel of T. Okay. Now what is beautiful here is it's simplicity. I mean, all of these elements here are relatively simple elements. There is nothing to it. And it really becomes even more apparent why we like this when we put what the demodulator looks like. So let's draw here. This is how you modulate. And let's draw a demodulator. So what the demodulator is going to do, it's going to receive this xc of t, and it will run that through an integrator, and then through a low-pass filter. So this is integrator, and this is a low-pass filter. Okay. Now, beautiful thing about this is look at the demodulation scheme here. It's asynchronous. You don't have to acquire the synchronization. Both of these elements just sit there, and they wait for the signal to come in. And then once the signal starts coming in, then they produce the output. So you don't need to acquire synchronization. Remember, in PCM, we are having ones and zeros coming. You have to know where the beginning of the word is, where the end of the word is, and you take, for example, these 8 bits and you turn them into a particular magnitude. And if you're 1 bit off, you're really making a lot of errors, right? Because you're taking the bits from 2 adjacent words that may be completely different than what your samples are. Here, you don't have to synchronize to the bit level. You're demodulating this asynchronously. You have no need for synchronization. The integrator just sits there, the filter sits there. Once the signal starts coming in, the signal starts coming out. If there's no signal in, there's no signal out. So nothing to synchronize to. As I said here, I mean, and I kind of drew, this is why my note in the comment in the notes. The notes assume that you are actually sending this to the line. You typically are not sending this. You're sending something like this. But this is, you know, you can apply this demodulator to either one of these. It's just a matter of what calibration. Go ahead.
On the demodulator, if it doesn't, has to know where to start from the beginning, because if it started at the bottom and here in the middle of that pulse train, you know, it's just ups and downs. You have to have a 0 point to start from.
Here's the what you don't see in this graph here. What happens if you started demodulating just from here, right? You're gonna have a DC offset, right? That you will have to deal with. But DC components in majority of signals is 0 anyway. So what you will do is, after a time, you're just going to correct for that DC, and you're going to go back to that C. It's not easy to see that in time domain. Think about frequency domain. Let's say I start demodulating the signal, but from here. What will end up happening is you will have this DC bias, right? That you can actually eliminate with something simple as this, right? Put the DC blocker, you know, in your receiver, and you're done with it. So it is what is actually important to capture is these variations up and down. The DC, you would correct it because the signal doesn't have a DC component. So just by removing the DC, you automatically get rid of random point, random bias that you have because you didn't start from zero here, right? Go ahead. Andy, did you have? No. Go ahead.
So then, what does the low pass filter do to the EC?
Well, the low pass doesn't do anything. Low pass here is for a different reason. Let me actually point why do we need low pass. There are, if you look at this waveform as I have it here, there are two things that you notice in terms of error, right? First error is, let's say the signal itself is changing slow. You know, so you can see that your modulation signal is oscillating around this one. So there is some rounding error that occurs every time. In an extreme case, let's say your signal is doing this. Your delta modulator is going to do this. So you're going to have some quantization error to deal with. This is what we call granular noise. And the purpose of the low pass is going to be to reduce that. So that's one of the reasons why you use the low pass. Right? So actually the reason why you use the low pass. What I need to do next is this. We need to look at the errors that occur here as a result of this quantization and modulation process. There are two types of error and characterize them both. One of them you already noticed. This is this guy. And the second one is what happens in this area of the curve. And what happens here is your delta is not fast enough, right? Because you can see here the signal is essentially running away. And even every time when you measure it, the signal x of t is lower, but my delta steps are not fast enough to catch up with it. This is called slope overload. And we need to characterize when does this happen and make sure that we prevent this from happening. Because this is something that we need to get rid of completely. And then for the cases where the signal is not changing and you still have granularity noise, we have to quantify how large that noise is. And you can see that, you know, even without any math, that trying to compensate for both of them simultaneously is contradictory. It's kind of one against the other, right? Opposing requirements. Why? Because to reduce this error here, what is your, if I want to reduce this granularity noise, what should I do with delta? Make it small, right? If I want to avoid slope overload, what should I do with delta? Make it larger, right? So which one I do? Well, that's what we need to design. And what is our design knob that we have? Well, our design knob is going to be this TS, right? By making TS sufficiently small, I can actually have a small delta and prevent the slope overload, right? Because I'm correcting fast enough that the small corrections will catch up.
How do you make it small enough? I mean, like, there's a delay on that. There's a like a time delay on that. So if you make that really fast, how do you make it really fast?
Well, in theory, I can do anything. So let's not worry about delay at this point. We'll worry about it in real world. But imagine, a lot of these modulation schemes are used for the signals at the baseband. And at the baseband, the signals are slow. Right, you're talking 4 kilohertz, 8 kilohertz, even 100 kilohertz, 1 mega. Right? All of that is slow with the contemporary equipment, right? Where we can, you know, sample at the gigahertz rate, right? So let's not worry about it. It's a valid concern, but what we need to do is wrap up some math, and then we'll kind of be able to do some engineering around all of these concepts here. So let's look at quantization errors in delta modulation. in delta modulation. We have two types of error. First one is granular noise. And the second type is slope overload. Okay. I think let us consider, and both of them are kind of illustrated here, right? You have your granular noise dominating this part of the curve, where the curve is relatively flat, and your quantized signal is bouncing up and down above the actual signal, and then the slope overload is happening here, where the signal changes faster than what you can catch it up by delta steps.
What if in some particular signal we not only have like just one slope like this, we have like a lot of slope. So there will be a lot of granular noise?
Well, this is just a section of the signal. You know, the signal goes forever, right? And you may have different types of errors in different parts of the signal. Let's first look at the slope overload. And what we'll have to do is we'll have to design our signals, design our delta, or find out what the constraint needs to be satisfied so that you never have slope overload. Slope overload is avoidable condition. This is not something that you have to have. If you design the system properly,
Yeah.
you'll be able to avoid this one. So let's first treat that one. So first I'm going to look at the second one, slope overload. And as I said, this one is avoided. To avoid, let me just put here, avoid. So what condition needs to happen for slope overload to not happen, right? What needs to be satisfied? Well, if I look at two adjacent samples, x of t minus or x of t plus ts minus x of t. So these are the two adjacent samples. One is taken at time x of t, the other one is taken at the next sampling interval. And I look at their delta, their difference. I need to then make their difference smaller than delta. If their difference is smaller than delta, in other words, if the change between two adjacent samples is smaller than delta, the slope overload never happens, right? Because the change is always smaller than the steps that I'm able to make. So they change, but I catch up. They change, but I catch up again. Every time they change, my step is big enough so that I catch up with the change. Now, if I divide both sides here with the TS, I end up with x of t plus TS minus x of t divided by TS. Needs to be smaller than delta over TS. And if I look at this thing here, then I can write something like this. X of t plus TS minus x of t divided by TS is smaller than dx of t over dt maximum, right? If you look at what is happening here is, as Ts is relatively small, then this is delta x over delta t, which can be approximated with the derivative. And I can say that this is always smaller than the largest derivative of x of t, right? So, this delta over Ts, I can write that as delta times Fs. So combining these two together, then I get a condition that needs to be satisfied so that the slope overload does not occur, is the delta derivative of x of t over dt maximum needs to be smaller than Fs times delta. So we have two, from this equation here, you have immediately what the cure for the slope overload might be. There are two cures. First of all, for any given signal, this is constant. This is the maximum slope that this signal may have. Right? So this, given a signal, I can determine what this is. And then I have two knobs that I can turn. If I fix my Fs, I need to make delta large enough. Or if I fix delta, then I need to make my Fs large enough so that this condition is satisfied. So you see, you should now see what happens. From the condition on a granular noise, I'm going to determine what is the smallest delta or the largest delta that I can use to have a signal to quantization noise ratio that's sufficient. Once I get the delta, this equation here will give me what Fs needs to be so that I never have a slope overload. Right? So you see how everything ties together.
Sir, if you increase the Fs, that is by decreasing the Ts, you might just again see granular noise at the slope.
Okay, so here are we have two types of error, right? This one. And we have three quantities that we're juggling. One is delta, one is Fs, and the third one is what? What is the third one?
T.
SQ and R, right? So these are the three quantities that I'm juggling, right? I pick two, and then I adjust the third one. If I pick SQ and R, and this is the power to noise in a case when you have a granular noise. If I pick this one, this would give me delta, and then from here, I'm going to obtain Fs, right? Okay? If I pick, for example, Fs and SQNR, then I can select the delta, right, and so on, right? So there are three things here that I'm going to be juggling to get what I need. I have two things that I'm trying to control and three knobs, but they're not independent. Most of the time, I start from here. I say, what is the SQNR that I need satisfied? And from there, I'm going to get delta, and then to prevent the slope overload, I'm going to select Fs or Ts, which is the same thing. So let me first look at an example, and then we'll go back to granular noise. So actually, I should do this. I'm going to still leave this graph.
Excuse me, Professor, I have a question.
Uh-huh.
Can you give us like a brief practical idea of the slope overload?
Yeah, that's an example.
No, I mean like in the real circuit, if we have like something like that, so how do we manipulate the delta as in SGNR and after that, something like that?
Well, let's look at an example. It's exactly doing that. I give you exactly the example here. So let's look at this example. Assume that x of t, your signal, is equal to a cosine 2 pi fmt, where a is equal to 1 volt, and fm is equal to 800 hertz. So this is a sinusoidal that you're trying to convert using, quantize using delta modulation. It says here, if delta, let's say delta is equal to 0.1 volt, so this is the size of your step. The question is, how large Fs needs to be to prevent the slope overload? Fs, right? Well, how large the Fs needs to be so that you never have a slope overload. So how do you deal with it? Well, we have this condition that delta of derivative x of t with respect to t maximum needs to be smaller than delta times f, delta times fs. Right? So let's look at dx of t over dt. That becomes a times 2 pi fn times sine of 2 pi fn t, and we can just put the minus here to make the math work. So what is the maximum of dx of t over dt? Becomes 2 pi a times fn, right? Because if you take the maximum absolute value of this is whatever is this magnitude here, because the maximum of this is 1. Okay? So that's this guy, and this needs to be smaller than delta times fs. Therefore, fs needs to be larger or equal to 2 pi fm a over delta. And in this case, this is 2 pi times 800 times 10, or was it 10 or 1? 1 over 10. 1 over 0.8. And this gives you 50.26 kilohertz. Okay? So that's how you would approach this, how you would determine what the fs needs to be. So you can see that fs is typically much larger than your Nyquist sampling frequency. Now, if you look at for voice, just to know, it has been experimentally determined that fs times delta over um needs to be greater than 2 pi times 800. So that's where fs is your obviously sampling frequency. This is the maximum magnitude of the signal, and this delta is the quantization step. Okay. So here, if for example you normalize your voice signal to be between -1 and 1, then if you give me fs, I'll be able to determine delta and vice versa. Okay, so that takes care of slope overload. Let's look at the other thing, which is granular noise. Now here, the thing is a little bit tricky, right? Because it's not easy to treat this analytically. And what I'm going to do is use your thorough understanding of the Fourier analysis and good intuition that you have, and kind of derive an expression that without much math, just by reason. You know? So let's take a look at how does this granular noise error look like. If this is your signal, it's changing slowly, and you look at your delta, here's your delta surrounding this signal. So if you plot this delta and you see what is happening, your error would always either be always smaller than delta and larger than minus delta. So it's always going to be captured between these two. You can never be more than delta away than your signal is. So you're going to be captured in between here. And if you look at the typical behavior, it's going to, if I bound this by these TS intervals, you're going to have something that looks like this. You're going to have a signal that is noise that is, kind of behaving like this. And I didn't do it justice because it looks pretty flat across the top, but it doesn't have to be flat. As a matter of fact, it's not, because delta stays flat and your signal is changing. So it looks somewhat like this, right? Somewhat random in these intervals, right? Now I messed it up completely, right? But you can see the signal changes rapidly every TS, but in between it's somehow however it is, and because it follows the difference between these two. So the difference changes as a signal itself. But it is quite, how should I say, fast changing signal. It changes every TS, and it changes even more in between these TS. So let's make some observation. First observation that I'm going to make is this. If I look at some distance tau, okay, then here's your intuition. How large does this tau need to be for the values here and here to be completely uncorrelated? In other words, if I set this tau to be some number, relatively small number, does what happened here has anything to do with what happens here? The observation you should make is that these are quite independent, right? We're talking about rounding error, right? Rounding error typically is independent from sample to sample, right? Because your delta is small. Whether you're on one side of delta of 0 or on the other side of 0, it's kind of flip of the coin. So your signal decorrelates relatively fast. In other words, if I'm looking at this, like if I block this, right? Would you be able to tell me what's happening here?
No.
No, right? And would you be able to tell me what's happening here?
No.
No, right? Why? So that kind of gives you an intuition. The signal decorrelates relatively fast. So if your autocorrelation function is narrow, which means the signal decorrelates fast, what can you tell me about power spectral density of this signal?
Flat.
It's very broad, right? So that's the first observation we make, right? So let me put that here. Signal decorrelates for small tau. So what that means is its power spectral density is broad, right? Right, so it's very wide in a spectral domain. So that's the first thing that we know about the signal. Observation 2. Let's consider what happens if, to granularity noise, if I change Fs. Okay? So I have two cases. All right, let me draw the first one, and I'm going to draw a really simple scenario where the signal is completely flat. Here I have relatively large delta, and here I have small, not delta, Fs, right? Here Fs is small Fs, and this is large fs, right? So this is x of t, and this here is x hat of t, and this is also x hat of t, right? Now, error here looks like this. So this is E of t, and then in this case, error looks like this. So this is E of t in this case. Now, let's look at the power of these two signals, E of t. What can you tell me about the power of these two guys? Are they the same? Square both signals and integrate the area under the curve. Yeah, they're the same, right? How about the power spectral density? This signal here changes much slower than this one. So the power spectral density of this guy is much more spread in a frequency domain. So here's what I'm trying to draw. If I draw a power spectral density of this guy, it might look somewhat like this. So this is SE, let's say E1 of F, sorry. This is F. And this is SE2 of F. This is E2. The area under the curve of these power spectral densities is the same. How do I know that? This is double-sided, of course. I'm just drawing one side. Why is the area under the curve the same? Because these two signals have the same power, and the power is the area under the curve of the power spectral density. Now, what will happen at the demodulator? Demodulator is going to be passed through a low-pass filter. So I'm going to pass this x hat of t through a low-pass filter. What the low-pass filter is going to do is going to pass only W through the filter, right? It will let only a portion of it will let the entire signal bandwidth go through filter, but only portion of the noise. In the case of this guy, it will capture this much power. In case of this one, it will capture this much of its power. So that's the second observation, that signal to quantization noise is going to be proportional W over Fs. So the larger Fs is going to be, the spreading is going to be larger. So the smaller this ratio is, the less of a noise I'm going to have. And now, observation 3.
Observation 2.
This is observation 2. So observation 1 is that the signal decorrelates for smaller tau. Observation 2 is that S and R is going to be proportional to this ratio. So I'm going to say observation 3 that the power only depends on delta, right? How large the delta is. Because in both of these cases, really when you square it, you lose the plus minus delta. It always becomes positive, and it only depends on delta. As a matter of fact, since it's a square, the power of the quantization noise is going to be proportional to delta squared. So I can, power of the quantization noise is proportional to delta squared. So here I can write power of the granular noise is going to be something that is proportional to delta squared and then proportional to W and inverse proportional to Fs, and I'm going to put some constant here to say to say proportion, right? So what is the value of this constant? This is now where the hard part begins, because the value of this constant k depends on the actual PDF of the signal itself. Now, if we assume that the signal is uniform, which is the same, the most simplistic assumption, and therefore this quantization error is uniform, and this is a good assumption for small delta, then we can actually calculate what the k is. So, assuming uniform statistics of the quantization error, uniform statistics of quantization error, one obtains that granular noise has a power which is 1/3 delta squared times W over Fs. And your SQ&R becomes 10 log of the expected value of x squared divided by power of the granular noise, which is 10 log of E of x squared minus 10 log of 1/3 delta squared times W over Fs. Is this the last page? Seems like. Yeah. Okay. So here's the equation that summarizes everything. It relates all of these parameters. SQ&R, delta, Fs, right? All three parameters. And you can add the slope overload one, which says dx of t over dt max needs to be smaller than delta times Fs. So these are the two equations that we use to characterize the delta modulation. Nominally, you start from this one. You say, what is the signal to quantization noise ratio that I need to provide for delta? And you can kind of calculate what this term needs to be. And then you have two equations. You have one equation that tells you the relationship with delta and Fs that comes from SQ&R. And you have another equation that tells you the relationship between delta and Fs. Two equations, two unknowns, allows you to solve for delta and Fs. Go ahead.
So both of the types of error, either granular noise or slope overload, I mean, like, they have three quantities: delta, Fs, and SQ&R.
Yes. Yes, and you have, usually this one is given, right? This is determined with the quality that you're trying to provide. Ultimately, this signal needs to be reproduced somewhere, and we need to have a sufficient quality to like the reproduction, whether this is voice or music or whatever the signal may be. So this is determined by our ears. I didn't say that, but for example, do you know what the signal to noise ratio needs to be for voice signal to sound acceptable for us? What does S signal to noise ratio needs to be for voice signal? Like telephone voice. When do we start objecting?
The frequency depends on the
No, what's the signal to noise ratio needs to be for? What do our ears sense? Signal to noise ratio needs to be on the order of 40 dBs.
Yeah.
Right? 40 dBs, So our ears are very sensitive. If you think about it, your signal needs to be 10,000 times better than noise, and before for you to deem that acceptable. Our ears are very sensitive, and if you look at
you know, from the strictly technical standpoint, they're more superior than our eyes, right? If you look at dynamic range and all of that kind of stuff. You know, in other words, if you go and look at the actual data, we could not be hearing better in terms of sensitivity than what we already are.
Oh, you talk about
Because we are very, you know, at around 1 kilohertz, between 1 and 3 kilohertz, we hear so good that if we were to hear a little bit better, we would start hearing the random motion of the molecules in the air, right? We are so sensitive in that range. So, you know, in that particular range, we hear very well. So, just to make long story short, so we as ultimate receivers, we judge what the SQNR needs to be, and that number is known. Like for good quality telephone voice, we need around 40 dBs of signal to noise ratio. So your signal to quantization noise ratio needs to be better than that, because you always know that the line will add some additional noise, right? So you cannot leave your transmitter with anything that's worse than what is minimally required by the receiver. So that's the starting point. And then you work from there. You say, okay, well, what is the bandwidth? I know that. That's, let's say, 4 kilohertz. And then you juggle these two. You say, what is the FS and what is the delta? And it turns out, when you design delta modulator, that you can get the same quality as the PCM that PCM has for 64 kilobits per second. You can get the same quality with delta modulation that's half that, like 32 kilobits per second. You can get the same quality. Plus, you get quite a bit of robustness, because what happens is, you see how delta modulator works. You're just sending these pulses, right? What happens if one of them turns, you know, up or down? Nothing major, right? You start deviating a little bit, you know, but what ultimately that does, it offsets you a little bit in DC, and that DC blocking circuit would get rid of that anyway, right? So you kind of have a self-correcting. So delta modulation can withstand quite a bit of errors. Whereas if you look at PCM, you're actually having numbers 0, 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 8. Let's say this is what you've sent. And what happens is the line turns this one into 1. Right? That's a significant thing, and you will start hearing that. So PCM on its own is very insensitive to delta, very insensitive to random errors, especially if it's not encoded in any particular way that minimizes the significance, relative difference in significance between these bits. Then your error at the most significant bit costs you a lot. In delta, you know, whenever you make error, it's just one delta up or down, right? So it is capable of standing, let's say, 10% of errors, or even 20% of errors, and it still comes okay on the other end. So that's why it still finds its applications in military, and you know, and in general in the applications that needs to be tolerant to noise, we use delta modulation rather than PCM.
Last thing, why we need to operate with slope overload? Why?
Why?
Say, why do we need to operate with the slope overload? We want to make it avoidable. Why?
No, it is avoidable. Why do we need to get rid of it?
Right.
Because what happens is, in the areas where you start having slope overload, your error becomes relatively large. It degrades the quality of your signal. Because if you don't have slope overload, your error is bounded between minus delta and delta. In a slope overload, it becomes larger than delta. Why? Because your signal changes faster than what you can keep up with. And that causes significant degradation in quality.
So in this case, granular noise in terms like acceptable in some.
This one is unavoidable. You have it. It's a quantization noise. The granular noise is a consequence that even with delta you have finite number of levels, right? You don't have any possible level. You can be this, or this, or this, or this, but you cannot be anything in between. And the signal travels in between. So the granular noise is the quantization error, the same
physics as the quantization error in PCM. That one is unavoidable as the consequence of you representing the continuum on the y-axis with a discrete number of levels. But the slope is the systematic thing that is just a consequence of you not dimensioning your system properly, and where the system is not capable to keep up with the signal. The signal is faster than what the capabilities of your modulators are. And that's what you try to avoid, and we know how to avoid it. You just have to do this. Okay, any other
Thank you,
questions?
sir.
All right, so we're kind of past this quantization. As of next lecture, we're going to start going into information theory. And we need that to understand how these ones and zeros can be encoded more efficiently. By, intuitively, you know that the signals have quite a bit of redundancy. So what we're going to try to do, exploit that redundancy to minimize the data rate that we need to represent the signal. And we're going to talk about these next week.